Right now, millions of people around the world are opening the Uber app at the same moment, each one instantly matched with a nearby driver, out of a pool of millions of drivers worldwide. This has to happen in under a second, every single time. How? I really want you to just think about that time frame for a moment. Literally 1 single second. In that incredibly brief window of time, a digital signal has to travel from your phone, through the air, hit a cell tower, route through miles of fiber optic cables, and reach a server that is likely hundreds of miles away from where you're currently standing. That server then has to sift through an absolute ocean of moving vehicles. It has to figure out exactly where you are, figure out exactly where they are, calculate the most optimal pairing, lock it in, and beam that confirmation all the way back to your screen. Doing this for one person? Well, it's a fun math problem. Doing this for millions of people simultaneously, without the whole system entirely collapsing under its own weight, that is an absolute engineering marvel. So how is this actually computationally possible at a global scale? How on earth do you find the single best match out of millions of moving vehicles in real time? If you've ever wondered about the invisible software engineering that quietly runs your daily life, you are absolutely in the right place. We're going to break down the exact mechanics of how this works under the hood in this explainer.
Okay, Section 1. The billion calculation problem and why naive search fails.
Let's dive right into this. To really appreciate the brilliant solution they came up with, you first have to understand why the obvious approach completely fails. In computer science, we call that obvious approach a naive search. If you were asked to build a ride-hailing app today, your very first instinct would probably be this naive search method. You'd say, all right, when a rider requests a car, let's just calculate the distance from that rider to every single driver who is currently online, and then we'll pick the one with the shortest distance. That logic makes perfect sense on paper, and to be fair, it works flawlessly if you're building an app for a tiny little town with exactly 3 drivers. But compare that naive search to real-world reality. At a global scale, you have millions of drivers constantly moving around. If you recalculate the distance to every single driver for every single ride request, the math just explodes exponentially. If 10,000 people request a ride at the exact same second and you have 1 million drivers online globally, that is 10 billion distinct calculations you have to perform in a fraction of a second. The server processing power required for that would literally melt your hardware. It's computationally impossible to do this fast enough. Let me give you a real-world equivalent of how crazy this naive search approach actually is. Imagine you have a terrible headache and you desperately need to find the closest open pharmacy. Using naive search is like picking up your phone, finding a master list of every single pharmacy in the entire country, and calling them up one by one. You call a pharmacy in New York, then you call one in London, then you call one in Tokyo, asking each and every one, hey, how far are you from my house? You do this millions of times just to eventually realize there's a CVS right around the corner from your apartment. It is a massive, completely illogical waste of time and server energy to check the entire world when you really only care about your own neighborhood. Which brings us to Section 2, the hexagonal grid solution, also known as geospatial indexing. This brings us to the actual engineering fix. The system doesn't check every driver. Instead, it shrinks the map. It builds a highly efficient system using something called geospatial indexing. Specifically, it uses an open-source system Uber created called the H3 library. Now, geospatial indexing is really just a fancy term for a very practical concept. It basically means dividing the entire world into a massive interconnected grid of small hexagonal cells. When a driver is out on the road, their phone is constantly sending raw GPS coordinates. Those coordinates are messy. They have lots of decimal points and are hard to process quickly. So the system doesn't save those exact coordinates for the search process. Instead, it converts that messy location into a simple, clean cell ID. It just says, driver A is currently in cell 402. When you request a ride, your location is also converted into a cell ID. Now the system doesn't have to search the whole world. It only looks at the specific drivers registered inside your specific cell and a few neighboring cells. You have instantly shrunk the search space from millions of cars down to maybe a few dozen. This brilliantly illustrates the beehive analogy. Think of it like a giant, invisible beehive laid right over the map of your city. Instead of trying to describe your exact GPS latitude and longitude coordinates to a friend, which takes forever, you just say, hey, I'm standing in honeycomb cell number 50. Finding someone nearby becomes incredibly simple. You only check your own honeycomb cell and the 6 cells directly touching yours. You don't scan the entire hive. By indexing the physical world into these simple, discrete buckets, the database can retrieve a list of nearby drivers almost instantly. Notice the specific shape they chose here. They use hexagons, not squares. Why not just lay a simple checkerboard grid over the map? Well, there's a fascinating technical quirk here that makes a huge difference. If you use a grid of squares, the distance from the center of your square to the center of a neighboring square changes depending on which way you look. The squares directly above, below, left, and right are one distance away. But what about the squares on the diagonals? If you remember basic geometry, the diagonal is significantly further away. That completely distorts real-world distance calculations and messes up accurate arrival times. But with a hexagon, the distance from the center of the cell to the center of all 6 neighboring cells is exactly the same. It's a perfect radius. It makes calculating distances flawlessly smooth and mathematically consistent across the entire globe.
Section 3. A match in milliseconds, the concrete walkthrough.
Okay, so we've got the grid, we've got the drivers inside the cells. Let's do a hyperfast walkthrough of a single concrete match to see exactly what this looks like in action. Let's start the clock. You're standing downtown. You open the app and request a ride. Boom. In milliseconds, your exact phone GPS turns into an H3 cell ID. The database instantly pulls up your cell, plus the 6 adjoining hexagons. It completely ignores the rest of the planet. Inside that tiny 7-cell cluster, the database finds exactly 4 available drivers. Now, instead of calculating distances for millions of cars, it calculates a precise, real-time ETA for just those 4 specific drivers, taking live traffic into account. It ranks them. It picks the winner. It locks the match and sends the ping directly to the driver's phone. The whole process takes a fraction of a second. You went from a global haystack to 4 needles, picked the sharpest one, and did it all instantly. Moving right along to Section 4, the efficiency plot twist, and why it's not always the closest driver. Now, you might naturally assume that the best match in that final step is simply the driver who's geographically closest to you. But here is the massive plot twist in all of this. The matching algorithm doesn't actually always pick the closest driver. Sounds totally counterintuitive, right? Why wouldn't you want the absolute nearest bar? Because the algorithm isn't just trying to solve your problem, it's trying to solve a massive optimization problem for the entire city. Sometimes assigning a slightly farther driver to you actually lowers the overall average wait time for everyone else nearby. Imagine 2 riders request a car at the exact same time. Rider A has a car 1 minute away and another car 3 minutes away. Rider B only has 1 car nearby. It's that same car that's 3 minutes away from Rider A, but for Rider B, it's 5 minutes away. If Rider A selfishly takes the closest car, Rider B might have to wait 10 or 15 minutes for a totally new driver to log on. This creates a cascading bottleneck. The system looks at this butterfly effect and balances the supply. It acts like an air traffic controller. An air traffic controller doesn't just send the nearest plane to the nearest open runway. Sometimes a slightly less convenient assignment for one plane keeps the entire airport running smoothly for everyone without causing a massive traffic jam.
If this is the kind of content you want more of, subscribing takes 1 second and it genuinely helps the channel grow.
Section 5. Staying fast at scale, handling millions of moving targets. So the grid logic solves the searching problem, and the optimization logic handles the matching. But we have to address a massive lingering question here. This isn't a static map of restaurants or post offices. These are cars, millions of them, and they are driving fast. Every single driver's phone is sending a new location update every few seconds. How does the system constantly update the positions of millions of items inside millions of grid cells without completely crashing the whole matching engine? The answer relies on 2 major infrastructure choices. First, you just can't save all this rapid-fire location data on traditional hard drives. Spinning disk drives or even standard solid-state drives have read and write speeds that are just way too slow for this. Instead, the system uses incredibly fast in-memory data stores. This means the current grid locations of all the drivers are held directly in the server's RAM. RAM is lightning fast. It allows the database to absorb thousands of position updates per second without breaking a sweat because it interacts directly with the processor. Second, you distribute the workload. You don't have one giant server in California handling the grid for the entire world. The system uses a technique called regional sharding. The hexagonal grid for London is managed by servers geographically close to London. The grid for Tokyo is handled by servers near Tokyo. By chopping the global map into separate, localized data centers, you ensure that high traffic during a rainy day in one city never slows down the matching speeds in another. Section 6. The universal search pattern. The crucial point I want you to take away here is that this elegant engineering solution, this exact combination of dividing the map into a grid, assigning cell IDs, and searching locally in memory, isn't just some proprietary magic limited strictly to ride-hailing apps. It's a fundamental blueprint in modern software design. This exact pattern powers a massive chunk of the digital economy. When you open a food delivery app, it uses this exact same grid indexing to instantly match your hot dinner order with the nearby couriers currently roaming your specific neighborhood. When you open a dating app and it shows you potential matches within a 5-mile radius, it is not calculating the distance between you and every single user on the platform. It's just checking the database for other users sitting inside your hexagon and the adjacent hexagons. Store locator features, local business review apps, scooter rental maps, literally any product with a Find X Near Me feature is fundamentally solving this exact same geospatial problem using some variation of this exact same grid-based solution. When you step back and look at the big picture, the contrast is incredibly stark. Under naive search, your search space is every single driver in the entire system. Under grid-based indexing, it's just the drivers in a few nearby cells. The speed of naive search at scale fails entirely. It's far too slow and requires way too much computing power. But grid-based indexing is near instant, even when you scale it globally. The update cost for naive search means recalculating everything every single time a car moves an inch down the road. Grid-based indexing simply means updating the cell ID for the specific driver who just crossed over a hexagon boundary. It is vastly more efficient, which is exactly why naive search is left to tiny local systems, while grid indexing quietly powers the massive global giants of the tech industry. We started this explainer by picturing millions of people around the world opening an app at the exact same moment, each one instantly paired with a driver out of a global pool of millions, all in under 1 single second. Now you know exactly how it happens. It's not magic. It's a combination of brilliant geometry, ultra-fast in-memory databases, and letting go of the naive assumption that you have to look at the whole world to find what is right in front of you. Which leaves you with one final question to ponder. If this staggering level of complexity is happening silently in your pocket just to get you a simple ride across town, what other invisible systems are quietly running your daily life right now?